George's Medical University, Lieutenant General Vipin Puri ji, faculty, students, alumni, ladies and gentlemen. Welcome to the third Dr. A.P.J. Abdul Kalam Oration, organized by King George's Medical University, Lucknow, through the Department of Medical Education. We all know Dr. Kalam, the 11th President of India, the renowned aerospace scientist, and the recipient of Bharat Ratna, the highest civilian award of our country. He visited our university twice, once as the President of India at our annual convocation, and again in the research showcase organized in 2009. This annual oration is organized in the memory of this great person in his birth week. Today, we are honored and privileged to have with us Padam Shri Professor K. Vijay Raghavan to deliver this oration. Dr. Vijay Raghavan is a distinguished professor and former director of the National Center for Biological Sciences. He served as the Secretary of Department of Biotechnology, Government of India from 2013 to 2018 and made major changes in the functioning of the Department of Biotechnology, which are remembered in the country. On March 26, 2018, the Government of India appointed him as the Principal Scientific Advisor to the Government of India. This is indeed an honor for a scientist of his repute. There, he was conferred Padam Shri on 26th of January 2013. He is a recipient of Infosys Prize in Life Sciences category. He is a Fellow of Royal Society and a Foreign Associate of US National Academy of Sciences. Dr. Vijay Raghavan did his graduation in chemical engineering from IIT Kanpur. Hence, he is our neighbor. We are in Lucknow, and Sir did it from Kanpur. He did his PhD in the field of molecular biology from Tata Institute of Fundamental Research. Thereafter, he did his postdoc fellowship in California Institute of Technology. His fields of specialization are developmental biology, genetics, and neurogenetics, and he is a scientist par excellence. He has to his credit many honors, many achievements. The list is huge, but I will name a very few here because I don't want to take from his time. He has fellowships of Indian Academy of Sciences and Indian National Science Academy. He is the recipient of Bhatnagar Prize for Science and Technology, Distinguished Alumnus Award of IIT Kanpur, Dr. J.C. Bose Fellowship, Fellowship of TWAS, the Academy of Science for Developing Country. Sir, we are eagerly looking forward to your oration on medical research and education during and after the pandemic. Professor Vijay Raghavan, sir, please.
Thank you very much, Dr. Shari. It's a great pleasure and honor to be here. And thank you, General Puri, for thinking of me for this very important lecture. As has been said, President Kalam is a great inspiration to all of us. He comes from a family of fisher folk in South India, in Tamil Nadu. And from there, he studied locally, went to the Madras Institute of Technology, and then joined what later ISRO, the Defense R&D organization, and he led many, many major projects. If there was a characteristic which he had, it can be summed up by saying that he was extraordinarily honest, full of humility, yet had the courage to take on big missions, get teams to work with him, and make those missions succeed without taking credit for them, having his team take the credit. And this is something which all of us need to learn today at a time when working together for a common cause is very, very important. The talk I'm supposed to give is about how medical education is to be reconfigured for the future. I know little about education and even less about medical education, so I'm not the right person for that. but I have broader views on how, in this situation, what we could do, and that relates to how we came about on this planet, how we are doing on this planet, and what we need to do. And from that context, education in general and medical education in particular follows as a particular direction. Now, if we look at ourselves, we can ask, supposing we were, looking at ourselves 30 years ago, we could ask, what should we do to have a better future? Perhaps we did not ask that question in a cohesive manner, and therefore we see in the entire world a situation where we have moved along over a period of 30 years in a manner which, is relatively random with consequences of great impact arising from that. Now we can ask now about the next 30 years or so how things will be. And what will the future be like or another about, let's say, 30 years. It's important to keep this in mind that humans have snatched nature's dice, as it were. Nature rolls out its dice every moment, but for some time now in human history, we have loaded the dice in what we call in our favor. With some luck and some ingenuity and some guile, we have explored nature's engineering and understood it substantially. The mysteries of, Jal, Prithvi, Vayu, Akash, and Agni, earth, the oceans, air, the skies, and energy, were seemingly ours and only ours to understand. In doing all this, we've also, in understanding nature's engineering, we have also become nature's engineers. Now we are stewards of the planet and we are faced with the responsibility of sustainable development for the entire planet while conserving biodiversity, the environment, and dealing with climate change. In this context, also we must keep in mind that we have developed extraordinary tools which are new and mighty and powerful. These are controlled by a few, promising to serve the many and rescue us all. And these are the tools, for example, of artificial intelligence and big data. Will all this take us and the planet to a new and bright future? Or will it create a dehumanized dystopia, as others predict? Is the questions we debate today, and the answers are in your hands as you educate the future generation. Now, if you look at where we came about as humans by an extraordinary accident. About 65 million years ago, a meteorite crashed on this planet and killed many, many forms of life, including the large animals, dinosaurs, who were dominating that space. The elimination of these large animals resulted in the growth of the mammalian radiation and us also. So we are here as products of an extraterrestrial crash. Now, while that happened, we also had more recently attempts as us as humans trying to understand how we evolved in this planet amongst other life forms. That was best articulated still by Charles Darwin, who went on a voyage in the Beagle in 1835. And he, along with separately with Alfred Russel Wallace, who did his research in the Singapore area, Singapore Malaya area, came about with evolution through natural selection as the way by which diverse life forms arose. Now, this is important to keep in mind because they are at the heart of what the theory of evolution says, is that all life on this planet arose from a common ancestor. And what we know today is that that common ancestry is connected by a shared chemistry, and that shared chemistry is connected by the thread of DNA. So, in understanding as medical students any life form, you will understand the details of other life forms. In other words, the tools we get to treat patients today come from studies on bacteria, on viruses, all the genetic engineering tools, for example, very large number of them actually come from studies of bacteria and viruses. In fact, this year's Nobel Prize for CRISPR-Cas9 came about by studying how bacteria resist viral infections. So, or viruses, take over bacteria despite, they're being resistant. So these kinds of interactions are very, very important for our growth of understanding and application. Now, Darwin's work was complemented by Mendel, who, without looking inside the organism, gave us the rules of inheritance a species. And these two, the evolution of speciation of species and the variation within a species, were integrated in what is called the neo-Darwinian synthesis, where we know that variations in DNA can give rise to both new species and variation within species. This understanding has grown enormously with the discovery of DNA as the genetic material, the structure of DNA, how it functions, and so on. So, again, this is an example of how medical education and medicine has been transformed completely by our understanding from fundamental biology. Now, these are two aspects humans have discovered, understanding nature's engineering from a life sciences perspective. But how did this come about? How did humans do this? As humans, we ourselves evolved by multiple kinds of accidents in this manner to become distinctive from our primate cousins, other non-human primates. That happened because our brain now is disproportionately large to our body size compared to other primates. How did that happen? That needs enormous nutrition. And one theory is that as we discovered fire, the ability to concentrate calorific value by cooking, we were able to provide the immense nutrition needed for our brain growth. If we had to do this by foraging alone, we would have had to, and by hunting also, we would have had to be eating almost 24 hours a day. So the ability to concentrate calories in a meal allowed us to both move from hunter-gatherers to domestication of communities, of plants and animals, and an increased brain size. That, combined with the ability to oppose thumb and forefinger, to make tools and to throw things, allowed us, and speech and language, our brain effectively being over-designed as a massively parallel computer, allowed the evolution of language and of cultural activities. So in other words, while other species evolved to survive on this planet, changes in us allowed us to use culture to not only survive, but to also dominate the planet. And cultural evolution took place much, much faster than evolution by natural selection. So social communities, sociology, economics, language, industry dominates the existence of human societies in a manner where our biological limitations are relatively lowered. A fruit fly can take off and fly soon after it's born, but a human baby can also take off and fly in an aeroplane. And therefore, we have overcome our limitations in extraordinary ways which were unimaginable before these. Now, these kinds of technological advances, of course, are impressive in many ways. They promised human society liberation from disease, poverty, and we see around us that that indeed has happened in many ways, but yet the numbers of poor and those who are unhealthy are still substantial. This has happened because while the absolute numbers of the more well-to-do, the middle class, those who are out of poverty is enormous and much more than any time in human history, the absolute numbers of the poor and underprivileged have also increased. This is because our size of population over the last few hundred years has grown enormously. Humans managed to do this, again, through technology by overcoming the limitations of getting food through agriculture and by domestication of livestock which were there in the early days of these two processes. Nitrogen, for example, was very, very limiting for growing crops on large scale because soil nitrogen was depleted and additional nitrogen would be needed for growing crops on large scale. Humans first got that nitrogen from bird droppings, guano, and when that started running out, from nitrite mines. And when that started running out, before around the time of the First World War, the Haber-Bosch process was invented, which allows the fixing of nitrogen from air and making of ammonia. That resulted in the fertilizer industry growing enormously, and therefore fertilizers became abundantly available. That and the damming of rivers, getting water at any time, the development of organic chemistry and pesticides allowed humans not to be limited by natural barriers to volume of food. And therefore, the agriculture industry and agriculture grew enormously. And this, today, for example, more than half the nitrogen in us comes from the Haber-Bosch process. The domestication of plants and animals, the growth of agriculture, and the simultaneous growth of engineering led to the first industrial revolution, and then to the next, and to the next, and to the next. And this runaway process has resulted today in an enormous ability to do major things to the environment. So we have moved, as it were, from being the consequences of surviving on this planet to become the wielders of the paintbrush, as it were, on the canvas of this planet. In addition to creating engineering structures of this kind and surviving on this scale, making, having industrialized agriculture, industrialized healthcare, militaries, and so on, our ability to make computers has also more recently changed the world dramatically. Many years ago, during the onset of during the Second World War, a team led by Alan Turing was trying to crack the Nazi code. And this team was, as I said, was led by Alan Turing. A little later, in 1950, Alan Turing asked an important question. He said, "Can machines think?" And this question, this paper titled "Can Machines Think?" came out in Computing Machinery and Intelligence, a journal, and it's something worth reading. It's a very short paper. And in answering this question, Turing said yes, and really created the field of artificial intelligence. Artificial intelligence aims to simulate human intelligence or replicate it in machines. But this is a very general definition. And today we have a dominance of what is called more like narrow artificial intelligence, where extraordinarily complex tasks can be imitated and learned to be done better and better. So what we really call artificial intelligence today is machine learning, and multiple layers of machine learning is called deep learning. And therefore, machine learning and deep learning dominates artificial intelligence today. Data is collected massively. Learning and test cases are used to improve recognition and decision making. And this has become a major prosthetic to humans in multiple kinds of decision making in all areas, including in science, in engineering, and in medicine. So this is going to be very important. Yet the question arises that, can this substitute for medical education? And the answer is no, because we must keep in mind that data has been called the fodder for artificial intelligence, or has been called the oil. But if I have oil or if I have fodder, I know what to do with it. But if I have data, I don't know what to do with it. If I have data, I must be clear that data is not information. I need to process that data and get information from that. For that, I need to annotate the data in some manner. And therefore, that is a very important point, again, in any area, including in medicine. So annotation and understanding of the source of data, its validity is very important. Information itself is not sufficient. Information is not knowledge. Knowledge is necessary to be got from information, and that is a very big aspect. Information has to be sifted through. We have to understand what is important, what should be thrown off, what is not, and that is also the next step in the processing of data to information. Even if you have knowledge, you need to get an understanding from that knowledge, and that requires decision making at a next higher level. If we have different sets of knowledge, we have to look at it in context in terms of previous knowledge in that subject. So the history of knowledge is important. And then we need to say, okay, with this knowledge, these are the kinds of interpretations possible. But knowledge, we must remember, is knowledge and it is not understanding. So we have to get understanding from knowledge, and that requires quite often human intervention to make leaps of faith and decide, well, this is what all the data says, this is the knowledge I get from it, but my understanding is that there's something very unusual is happening. And we now have a situation that we have two kinds of big data collection. We are collecting data available all around us, in the from which we don't generate. These are, for example, telescopes look at data from all over the universe. They can look at data from under the ocean, in the oceans, and so on. But humans also generate a huge amount of data, and this data comes from hospitals, from the transportation industry, from our high energy physics experiments, such as in Geneva, and so on. So we need, therefore, in the analysis of data, both from natural sources and what we generate, a very critical component, which so far machines cannot yet give. And even if they give, we need to work in a manner which keeps human presence substantially strong. And this factor, which is needed in the analysis of everything, is called intelligence. Intelligence is something which is not given, it is something which comes from training, practice, peer groups, use of various tools such as computers and so on, but not computers cannot give you the intelligence. Intelligence comes from huge cultural interactions and communities. And therefore, for medical education, those kinds of interactions are absolutely necessary and important. So in that situation, we have to say, what are the key questions in education do we need to ask of data today? We need to ask, and this is relevant to all of education, what is the provenance of data? Where does it come from? Is it well annotated? Is it good? Is it, junk? And so on and so forth. Secondly, what are correlations and what is causal, right? Just because Tamilians eat dosa, dosa doesn't cause Tamilians. There's a correlation between dosa and Tamilians, but it doesn't mean that there is a causal link in being a Tamilian from dosa. So we have to understand that, and that comes from an understanding of culture, society, language, and so on and so forth. Which way does causality go, and what is causality and what is correlation? The next point is we have to understand from this, looking at the data, distinguishing between correlation and causality, how it helps us act. Now, many of these kinds of decisions can indeed be done better and better for routine matters by computers, but a computer and a human interface is what is absolutely necessary, at least an understanding with in depth about what the computer is doing. And therefore, in terms of medical decision making, in terms of medical education, training in the mathematical sciences, in statistics, robustly is very critical, and also in computer sciences and understanding. Otherwise, you will look at a device and say, this is what it is telling me. And that today, any citizen can do. And a trained doctor needs to be better at that 10 times, 100 times. And therefore, it's very critical that training in these areas are also included in medical education. So technology has dramatically changed our access to data. And this is very important in every area. And it helps us understand we have to ask how it helps us understand the universe better and how can we use it. So it gives us access to data across scales. But the question is more better? From the nanoscale to the system level, there are many examples of the success of big data. But our question is, have just the low-hanging fruit been picked? And where do we go from here? Big data can be extraordinarily valuable, And those who bemoan its onslaught are just wrong. You cannot replace big data by some deep intuitive thinking alone. And as people in the life sciences, as the famous life scientist Sidney Brenner said, we ask only a few questions on data. And he said that we are thirsting for some theoretical framework to understand big data. Many believe that more is better, but history tells us that least is best, and we need a theory and a firm grasp on the nature of objects we study to predict the rest. Now, this is tough for medicine because medicine and biology are deeply linked, but they are linked in a manner similar to physics and engineering. Medicine is the ability to use the principles of biology to get things done on the field. And just as you don't have to know every aspect about the theory of relativity and Newton's laws and atomic physics while constructing a bridge, you can rise to a level of physical approximation, but engineering precision to make a high quality bridge. In a similar way, you could learn, combining from what we know from biology and from medical practice, what improved medical practice is. But this link needs to be constantly there, and we must ask what is the central theme for that link between life sciences and medicine. And unless we understand that and are really well structured in that, we are not going to, we are going to be medical scientists, we are going to be clinicians without understanding the fundamentals of science, or we're going to get into a situation where we're focused on the fundamentals of science and not looking at medical aspects. So clarity should come on what is the correct level of understanding which medical students should have. I'd like to end here by saying that the sources and analysis of data allow an extraordinary opportunity for this middle level to be done in medicine, just as it allows that same middle level to be explored between physics and engineering or chemicals and chemistry and chemical engineering and so on. In other words, the acts of doing in terms of public, in terms of society, in terms of economy, must also be deeply connected with the level of understanding, but it should be connected at the right level, not at too fine a level, which makes it useless for application, or not have application without an understanding of principles. Where does that mean? So big data allows us to do two things. First of all, it allows us to understand what does this mean by other people analyzing the data and telling us on our phones. But that's not good enough. That's okay for certain kinds of areas which are not your core. In your core area, you need to have a deep, deep understanding. And therefore, the development of tools which integrate all of cell biology, because cell biology is the core of medicine, groups of cells interacting on one another with one another to give outcomes is very critical. People, animals, plants, bacteria, viruses interacting with the ecosystem to give rise to these interactions are very important. So ecology and evolution are very important. And all of this is linked, as I said, by the thread of DNA. So how does one put all this together? We need tools developed, and we also need understanding of scientists so that on your phones you can have apps which can take you through a walk through any part of the cell of any part of the human body, any cell, any tissue, to see what is happening in health and in disease, in infection, in a manner where it requires you to have a core understanding. At a very light layer, the public can see this and get an understanding of what's happening. But that soft touch app kind of layer is not enough. You must have a core understanding of every area. Just like you, when previous generations growing up looked at Gray's Anatomy, you had books on physiology, you had books on biochemistry, an integrated book which allows you to look at every aspect of life interacting with the patient needs to be there, dynamically upgraded and always available. And today's tools allow that. So I know that all of you are going to be working on how medical education should be, what you should do next year, how you should pass your exams and these will happen and these are good. While doing that, we must get together a group of medical scientists, clinicians, doctors, and life scientists together to have this dynamic high quality educational material in every language with great depth and also great breadth available. This is not an easy task. It is not. It's similar to building a major a nuclear research station in CERN in Geneva, but it's very different in the sense it's a much different kind of collective endeavor. These are the kinds of efforts which I think India can take up and do really well. They're difficult, they're challenging, they border on the impossible, but when done well, it can bring the learning of medicine to every single doctor who's studying in their own language also. Thank you very much.
Thank you very much, sir. We request our Honorable Vice Chancellor to give you a virtual memento and a virtual certificate, Abdul certificate, and we will send it by post to you, sir. This will be followed by presidential address by our Vice Chancellor. This is the certificate of Dr. A.P.J. Abdul Kalam and the memento, sir, which we will give you. Thank you very much, sir, for accepting it. We will send it by post. Now I request Honorable Vice Chancellor, sir, so please
Thank
give us
you.
interest.
Madam Shri Professor Vijay Raghavan sir, ladies and gentlemen, education is the most powerful weapon you can use to change the world. Bharat Ratna late President A.P.J. Kalam once said. Ladies and gentlemen, it has been an absolute pleasure and academician's delight and a treat to hear out Padma Shri Professor Vijay Raghavan on this very fascinating subject, which is indeed so contemporary, so relevant, and so interfaced and intertwined with our present academic ecosystem. Professor Vijay Raghavan sir, with your permission, would like to reflect for a wee minute, for 2, 3 minutes, on the KGMU experience on this subject. I'm talking very specific on medical research education during and after the pandemic. Both education and research in the university underwent a radical makeover in the wake of the pandemic, with bedside clinical teachings shifting to virtual didactic lectures. The undergraduates had an initial suspension of classes followed by online teaching, but was punctuated with major interruption of programs, lack of skill training, blurred timelines, with faculty initially ill at ease on online teaching, as you reflected, which is so important in the times to come to develop, and also the fact that the online teaching was not interactive was an added predicament. But having said all this, we knew that we had been pushed into a new modality of online teaching, which required greater faculty preparedness, and we knew that this would be the way to go in times to come. The postgraduates at our university had their own share of issues. There was no exposure to routine emergencies, COVID duties, and stress associated with it was an issue. Postgraduates were unprepared for pandemic work. Thesis work was delayed. The flip side was that the pandemic experience was once in a lifetime. They learned e-learning became a new way of life, developed skills for self-preservation in these difficult times. When we looked at research at the King George Medical University, we found that there was a setback of ongoing non-COVID research projects. Everything just stopped. There was focus on COVID related research. Newer collaborations were being formed. King George Medical University being one of the largest medical universities in the country, there were multiple collaborations formed. And as Dr. Vijay Raghavan said, we did collaborate with many universities across the globe, especially in artificial intelligence and the other associated issues. We got free access of global COVID research advancements, including vaccine development. So a lot of things happening in this university. Besides, newer modalities of treatment were identified, strengthening the need for innovations to move at a fast pace. And actually, translational research in its true terms was staring at us. Post-pandemic, friends, ladies and gentlemen, Professor Raghavan sir, education and research will take a long time to normalize, maybe 1 to 3 years. E-learning will continue and expand and become a way of life. And I sincerely believe what you said, the machine-man interface has to be consolidated. And there is a crying need for us as medical professionals to understand that medical informatics, artificial intelligence is going to be a way of life and has to be used by us effectively if we want to improve our overall results. I think health of a nation will get the attention that it deserves. Maybe this is a fallout of the pandemic. And health budgets across the world will get an impetus. Pandemic preparedness will become integral to health policies of a nation. At least we hope so. In conclusion, then, ladies and gentlemen, I once again thank Padma Shri Professor Vijay Raghavanji for drawing a roadmap of medical education with a visionary prism and helping us to understand perspectives, challenges, and the way ahead in this digital age. The KGMU family expresses its heartfelt gratitude to you, sir, and to express our deepest and profound appreciation, I request the faculty of KGMU to rise for a standing ovation for what has been a marvelous exposition of an oration par excellence. Ladies and gentlemen. Thank you once again, sir, for sparing your time and for this wonderful oration.
Thank you very much, General. It's a great pleasure to be here. Thank you so much. Bye-bye.
I have the pleasant task of vote of thanks. The last few years has seen a lot of development